So remember when we did just an area and we created a Riemann sum with a bunch of rectangles? What would happen if we took one of those rectangles and rotated it around the x-axis with the rest of the shape? What would it turn into? Well, it's going to be a short, flat cylinder. See, we know how to find the area of a cylinder. If you think about what we did with Riemann sums, we took an area that we knew how to find, that is a rectangle, and used it in a limit to get an area that we didn't know how to find, which was a parabola shape. Now we're using a volume that we know how to find, which is a cylinder, and we're using that to find the volume of something we don't know how to find, which is this bell-shaped parabola thing, right? Put a little stick on there and go bing, 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 bing. It's a bell. All right. Now, my attempt to draw this might fail. Just a fair warning. I'm going to try and draw it. The big, very flat cylinder. And since it's big and very flat, it's usually wide, I guess I could say. It's very wide and very flat. So we usually call it a disc rather than a cylinder. So, it's like, it's okay. It has two edges. I've failed the back of it completely. All right, so what we're going to usually do is we're going to pull this out and say, let's look at this shape, and I'll look at it in miniature so I can make a nice picture of it. It's a little disc, okay? And then we can sort of analyze it separately. But you want to remember that this is happening to all of the rectangles, not just one of them. So you can sort of look on the internet. I was trying to find some decent pictures of this rotated. Here's the sort of best I can find. It's not a paraboloid. It's not the same shape, but here's the idea. Right? The idea is you take all those rectangles and rotate them. That's the idea. Now, so when we did Riemann sums, we called each rectangle we called a sub I, right? And then we could say a sub I equals f of x sub I delta x. And then from that, we got our integration that the area is equal to the integral from a to b of f of x dx, right? That's what we did with areas. So that's the sort of 2D version of it. So in 2D, we have these things. All right, we have an a sub I, it's equal to f of x sub I delta x, and we use that to create the integral from a to b of f of x dx. So what we're going to do with our representative volume slice is we're going to call it v sub I. So the ith, so often called the ith volume element. As the a sub I is often called the ith area element. This is the ith volume element. So the volume, somewhere in the middle. All right, so what is that volume as it depends on the x sub i's? Well, this is a cylinder, so it's v equals pi r squared h. So the question becomes, what is the radius of the cylinder? All right, so v sub I is going to be pi times what? Well, the radius of the cylinder, if this is x sub I right here, then the radius of the cylinder is just the height to the curve. So that's going to be f of x sub I. Just like the f of x sub I is the height of the rectangle, right? F of x sub I is the height of the rectangle. F of x sub I is then also the radius of the circle, because it's also up here. All right, so the radius of the circle is f of x sub I. But I got to square it because it's part of the volume formula for a cylinder. Now, what's the height of this cylinder, which, by the way, in this picture, really looks more like a width. So what do you think is the width of that cylinder? Well, what was the width of the rectangle? The width of the rectangle was delta x. The width of the cylinder is also delta x, right? So that width is delta x. And this radius is f of x sub I. So that's your ith volume element. V sub I is equal to pi f of x sub I delta x squared. So then, just as here, what you're really doing to get from this ith area to the total area is you're doing a limit as n approaches infinity, the number of rectangles. Because there's a lot more going on than that, but this is the essential guiding process. So we're going to take the limit as n approaches infinity. Well, as we put in infinitely many rectangles, what we're going to end up with is a formula for volume, which is that V is equal to the integral from a to b of pi f of x sub I squared dx. So the delta x becomes dx, just as this delta x becomes dx. The f of x sub I becomes f of x. The f of x sub I becomes f of x. And all the other features remain. I usually put these brackets here. Some people just put the squared on the f, I think it's a little clearer if I do that. The other thing that I can do is pull out the pi, because regardless of what the shape, if I'm rotating, I'm going to have cylinders, the area is going to have pi in it. Let's just pull that out. So the volume is now pi f of x sub I squared dx. All right, well, how hard would it be to do that volume for this particular shape? All right, so we're always going A to B. So what are our A and B? So this is our A is 0, and this is our B is 2. Right? So that means that the volume of this shape is equal to pi times the integral from 0 to 2 of this function 4 minus, I messed up my minus sign, 4 minus x squared, but then squared dx. All right. Now, you can handle this integral any number of ways, and so that's what we'll do in our, well, should I do it now? No, this video is getting kind of long. I will do the integral, and you can do the integral, and then compare in the next video to see if you get the same thing I did.